Mini Lesson 1A, Functions, Regressions, and Predictions. Determine the type of function, exponential, linear, or quadratic, that best models each scenario. Provide a reason to support its appropriateness. Formulate a model based on the function type and use it to make predictions. The value of a piece of car was $21,000 when it was purchased. During each 1 year period after the car was purchased, the value of the car at the end of the period was 15% less than the value at the beginning of the period. Formulate a model and use it to predict the car's value after 5 years. The function type here is exponential. One way we could determine this is because it's talking about percentages less at the beginning of the period. So it talks about rate of decrease, and that's why we could say it's exponential. Let's see, a model based on this function type, we'd have y equals a times b to the x power, where a is the initial amount and b is the growth factor. So in this case, a is going to be 21,000 and b is going to equal 1 minus 0.15. Our equation is going to be f of t equals 21,000 times 0.85 to the t power. They want you to predict the car's value after 5 years. So we're going to evaluate when t equals 5. From there, we could put this into the calculator. All right, once we put it into the calculator, we get about $9,317.81. During UTA's 100th year celebration in 1995, students recorded the population in Arlington, Texas, which was approximately 290,000. From 1995 to 2025, the population of Arlington increased by 39.7%. Create a model and use it to predict the Arlington population in 2030. This one is also exponential. It's talking about a rate of increase. To find this rate of increase, well, first we know that the initial value was 290,000. But to find the rate of increase, we know it's 39.7% for those 30 years. We want to use the common ratio formula. R equals y2 divided by y1 raised to the 1 over x2 minus x1 power. That means that y1 is going to be that 290,000 and y2 is going to be a 39.7% increase from that. So it'll be 290,000 times 1.397, which gives you 405,130. X2 is the 30 years, and X1 is 0 years from 1995. If we plug that into the formula, we get about 1.011206564. Or we could just leave it in this form to have a more precise answer. We want to know the population of 2030, so we're going to find f of 35. We have 290,000 times the 405,130 over 290,000 raised to 1 over 30 power. And when you plug this in, you get about 428,345 people. A runner is timing their laps around a track. The runner took 15 minutes to run 4 laps, and the runner took 40 minutes to run 7 laps. How many minutes should it take the runner to run 1 lap, and use it to determine how many minutes it will take the runner to run 105 laps? This function is linear. The runner is assumed to be running at a constant rate of change here. To find this average rate of change, we're going to use a slope formula. M equals y2 minus y1 over x2 minus x1. We'll say this is x1, y1, x2, y2. Plugging this in, we have 7 minus 4 over 40 minus 15. 3 over 25. So this is saying it's 3 over 25 laps per minute. We want to know how many minutes it takes for 1 lap. So if we have 3 laps for 25 minutes, 1 lap would be some other kind of minutes. We can cross multiply these. So 3m equals 25 divided by 3. So that means that it is 25 over 3 minutes per lap. Now to find the amount of time for 105 laps, we would just multiply this by 105. This would be 875 minutes. And then if we want to convert this to hours, just divide it by 60. So it means it should take about 14 and a half hours. If we would say that each lap is a quarter of a mile, the 105 laps is about a marathon. After sales tax, the price of an orange chicken bowl at Panda Express in 2010 was $5.40. The price of that same bowl in 2025 is $9.42. What is the growth percentage, and use it to determine the price of an orange chicken bowl in 2030? This is exponential. It's talking about growth percentage. We want to find that growth percentage, so we're going to use a common ratio formula again. Y2 is the more expensive one in 2025, and then Y1 was the original price, $5.40. X2 is 15 years after 2010, and then X1 is going to be 0 years after 2010. Plug these into the formula to find the growth factor. We plug it into the calculator, you get about 1.038. Now we'll plug that into the formula with the whole exponential function. And since we're looking for 2030, that's 20 years after 2010. Let's plug that into the calculator. So the predicted amount, the predicted cost of an orange chicken bowl at Panda Express in 2030 is $11.34. A ball is thrown into the air with an initial height of 4 feet. The ball reaches its maximum height of 20 feet after 3 seconds. The ball is then caught with a terminal height of 4 feet 6 seconds after the ball was thrown. Create a model and use it to determine the height of the ball after 5 seconds. If we sketch this out, the initial height was 4 feet. The maximum height was 20 feet after 3 seconds. And then the ball was caught at 4 feet again 6 seconds after it was thrown. This is a quadratic function. It talks about gravity, a ball being thrown. Since we're given the vertex, the maximum height, we could use this formula to determine our equation. H will equal 3, K equals 20, and we don't know what A is yet. So let's plug in one of these two other points. Let's go ahead and plug in this initial value. So we'll say x equals 0 and y equals 4 to solve for A. Four equals A, parentheses, 0 minus 3 squared plus 20. Let's rewrite that over here. 4 equals negative 3 squared is 9, 9a plus 20. Subtract 20 from each side. Divide by 9. And so a is going to equal negative 16 over 9. Now that we have the formula, we want to find the y value when x is 5. And we'll plug this into the calculator. And then we get about 12.9. 12.9 feet. Let's look at the next page. Reading scatter plots and residuals. Pseudasticity, dispersion or variance. Homoscedasticity, the characteristic of a model having a constant variance of its residuals throughout the entire range of predicted values. This occurs when the difference between the actual values and the predicted values of the response variable does not have increasing or decreasing trends. And heteroscedasticity is a situation where the variance of the errors in a regression model is not constant across all values of independent variables. This can indicate that this is not the best model or vital information is missing. Here are the different types of residual plots that you may see. We have unbiased and homosedastic, and then we have ones with patterns. The residual plot that you would want to see for it to have the strongest case would be this one that seems to have no correlation. The other ones seem to have some kind of correlation. This looks like a positive linear. This one is a curve. This one looks like it's going out into several directions. It may be a better fit than the others, but still, it's not as scattered as the first one. This one's positive. This was kind of going up and then over. So remember, this is the best residual plot for it to have a strong correlation. In addition to looking at residual plots, you could also look at the correlation coefficient R, Pearson's number, a statistical measure that quantifies the strength and direction of a linear relationship between two variables. And you can also look at the determination coefficient, R squared. It quantifies the proportion of variance in the dependent variable explained by the independent variable. Now, for example, quadratic functions, you will not see a correlation coefficient, but you will still have a determination coefficient. You could also see the residual plots for any of these regression models. Now, for correlation coefficients, if it has -1, that is a strong negative correlation. The recorded values would make a straight line in that case, going down. Now, if it's between -1 and -0.5, it's considered a strong negative, but it's not perfect. And if it's in between -0.5 and 0, it'd be a weak negative. No correlation is when it's all scattered. Now, we don't want that with the actual scatter plot, unlike the residual plot. And then the positives would be anything greater than 0, 0 to 1. For regressions, use Desmos to calculate these formulas. You will not be expected to calculate a regression model by hand that doesn't fit perfectly. Runner walker training for a marathon. This table has a runner and it says how many minutes it takes them to go a certain amount of miles. Now, to find the linear regression equation, we want to put these into Desmos. Since it's giving us the miles, let's go ahead and say that miles is going to be our independent variable, x. And so our dependent variable in this case will be minutes. To find the regression on Desmos, you will click the plus sign and then go table and then type in your values. Once you have typed in the values, double check that everything is inputted correctly. Once you've done that, click the regression icon next to the table, and it says linear regression. You could change it to a different regression depending on what you're looking for, but right now we're just going to do linear. It has our equation, our determination coefficient, and our correlation coefficient, and we could plot our residuals. Let's go ahead and record the equation and the coefficients on our paper. All right, so looking at our correlation coefficient is 0.9882. That is a strong positive. Look at the residual plot, the red points. It looks like a lot of them are clustered here, and then they kind of go down and then back up. Let's sketch a picture of that on our paper. So for the description, we can say it's clustered at the beginning. Goes down and then up. This would overall be an okay model here, but it just might need some more data points. Arlington population. We have the year, the T years after 1895, and then the population. We're going to use an exponential regression equation for this one. Now, the x value is going to be the T years after 1895, and then the population, we're going to say that's the y value. We don't want to use the years as in 1895, 1900, that sort of thing, because you'll have a bunch of answers that are in scientific notation. And it'll overall be just harder to read. All right, so 30 plus 5, 35, and then just fill in the rest of these on the table. All right, for the exponential regression equation, we'll put these into Desmos and do something similar to the previous example. Oh yes, and then for the hours to run or walk a marathon, you would plug in 26.22 miles into the formula, which is about 466 minutes. Divide that by 60 to get about 7.8 hours. All right, so to get the exponential regression, let's go ahead and delete these. Click the plus sign for table, and then input all of your values. When you're putting these in, make sure you don't write any commas in there or it'll say error. Once you've entered in the values, double check that you've plugged in everything correctly. And then click on the regression icon. And now we're going to click on where it says exponential regression. So we get an equation that looks kind of like this. If you look at the residual plots there in the red, They're kind of really far below the line and far above. Let's go ahead and record this one on our paper. All right, and then it says, what is the expected population in 2030 when t equals 135? For x, we'll put 135. The expected population is to be around 522,654. If we refer back to a previous example, this number is larger than the one from here. But notice that the data collected for this problem is only from 1995, whereas this data that was collected is for a whole 100 more years. That shows and indicates that the population growth is not increasing as fast as it was before. Let's sketch the residuals. Let's refer back to the Desmos graph. If the plots are not all showing up, you could go to the toolbar, and the X values that you would want to set is just a little bit smaller than what you have, and a little bit larger. The Y values, make sure that they're visible as well. But don't go too far out of bounds for either of the axis windows, or it will look like a straight line. Now, it's scattered right here and scattered up here and down there. This shows that it would be a decent indication of it fitting, this model fitting the actual values. So we can write that overall, the residuals are scattered. Dropping a ball from an airplane. This was going to be a quadratic regression. We're going to say that the seconds is x and the height is the y value. So we'll plug these into Desmos and use the regression calculator to find the equation. All right, let's delete these, add a new table, and then plug in all the values. Make sure you don't put any commas into your values or it'll say error. Once you've inputted values, double check that they are in there correctly, and then click on the regression icon. Now we're going to click on quadratic regression. Let's plot the residuals. Go ahead and write these on your paper. Using this model, when is the ball expected to hit the ground? To find this, we're going to set y equal to 0 and find the intersection. So we've graphed these. It looks like it's expected to hit the ground around 51.3 seconds. And then let's sketch a residual graph and describe it. Let's go ahead and have a window that will show the residual plots. Looks like we want x to be between about, let's say, -5 and 60. And then the y values from 0 to about 45,000. Let's have the y values go a little bit lower. So I have like negative 3,000. Just so we can see those residual plots better. Looks kind of like a straight line from here. So in here, there could be a pattern, but not necessarily since they're all so close to 0. Alright, so let's go to this Desmos page specifically. And this Desmos page takes you directly to the years and minimum wages already graphed. So use all the regression formulas available on Desmos. Which one seems to fit the best and why? Go ahead and write those down. You can use reasonings for it with the residual plots or the determination coefficients or the correlation coefficients. And then whichever model that you think fits the best, use it to predict the federal minimum wage in 2026. Looking at all these models, these are the predictions for each of the models for the minimum wage for 2026. Which model do you think is actually going to be the most accurate? It's quite possible you'd want to throw out the quartic regression since it is less than what it is currently. But you might also want to accept it since it's the one that's the closest to the current. Whichever you choose, go ahead and write that on your paper. In 2025, the median wage in Arlington is $34,549 less than living wage. This means do not accept a full-time job for under $23.86 per hour.